Hello friends, welcome to the lecture on linear dependence, independence and Wronskian of functions. First of all, we will define what do we mean by homogeneous and non-homogeneous linear differential equations. The nth order linear differential equation is given by a naught x into by nx. By nx is the nth order derivative of y with respect to x plus a1x by n minus 1x and so on anx into yx equal to rx, where aix I equal to 0, 1, 2 and so on up to n are continuous functions in an interval I, and the coefficient of by n x, which is a naught x, is assumed to be not 0 for every x in I. So this equation, the nth order linear differential equation given in 1 will be called a homogeneous linear differential equation provided Rx is identically 0, and otherwise it will be called a non-homogeneous linear differential equation. Regarding the homogeneous linear differential equations, there is a very nice theorem which we call as the superposition principle for homogeneous functions. It says that let by 1 by 2 by k be k solutions of the homogeneous nth order differential equation 1. We are considering homogeneous equation here, which means that we are taking Rx to be identically 0. So in the case of a homogeneous linear differential equation given by 1, if we have k solutions by 1 by 2 by k, then they are linear combination. Linear combination means the function c1 into y1x plus c2 into y2x and so on ck into ykx, where c1, c2, ck are arbitrary constants, is also a solution on I. It is very simple, we can easily prove this. Let us see how we can prove this. Our homogeneous differential equation is a naught x into by nx plus a1x into by n minus 1x and so on a naught a n x into by x equal to 0. This is our homogeneous linear differential equation. So let suppose by 1 by 2 and so on by k be k solutions of this equation. This equation, then we will have a naught x into by 1 n x plus a1x by 1 n minus 1 x and so on a n x into by 1 x equal to 0. Similarly, for the function y2x we will have as we can write in a similar manner the kth equation a naught x by k n x plus a1x into by k n minus 1 x and so on a n x by k n by k x equal to 0. From these k equations, then we can show that c1 y1 plus c2 y2 and so on ck by k is also a solution of this homogeneous equation. So then a naught x into c1 by 1 plus c2 by 2 and so on ck by k, the kth derivative of this, that is dk. No, we have here nth derivative. So nth derivative of this a naught x into nth derivative of c1 y1 plus c2 y2 and so on ck by k plus a1x into n minus 1th derivative of C1 by 1 plus C2 by 2 and so on Ck by k, and the last term Anx into C1 by 1 plus C2 by 2 and so on Ck by k. This is equal to A naught x. Now nth derivative of C1 by 1 plus C2 by 2 plus Ck by k will be C1 times nth derivative of by 1 plus C2 times nth derivative of by 2 plus Ck times nth derivative of by k. Similarly here n minus 1 of the derivative of this linear combination will be C1 times n minus 1 of the derivative of by 1 plus C2 times n minus 1 of the derivative of by 2 and so on Ck times n minus 1 of the derivative of by k. So we can write it as equal to C1 times A naught x n minus nth derivative of by 1 this plus C2 times A naught x into nth derivative of by 2 plus A1x n minus 1th derivative of by 2 and so on A1x by 2x and so on. We can write Ck times A naught x by k n x plus A1x by k n minus 1x and so on A n x by kx. Okay, now since by 1 by 2 by k are solutions of the given equation, homogeneous equation, so this is 0 and this is 0 and therefore we have 0. So C1 by 1 plus C2 by 2 and so on Ck by k is also a solution of the homogeneous linear differential equation. So this is known as the superposition principle for homogeneous equations. Now let us define linear dependence and independence of functions. It is a very important concept in the solution of differential equations. So a set of functions by 1 by 2 by n will be called a linearly dependent on an interval I if we can find some constant C1, C2, Cn not all 0. That means at least one constant here must be a non-zero constant such that C1 by 1 plus C2 by 2 and so on Cn by n equal to 0. So if the n functions are not linearly dependent, then they will be called linearly independent, and for that we have the definition that C1 by 1 plus C2 by 2 and so on Cn by n is equal to 0 will always imply that C1 equal to 0, C2 equal to 0 and so on Cn equal to 0. That means we cannot find any set of n constant C1, C2, Cn not all 0 such that C1 by 1 plus C2 by 2 plus Cn by n equal to 0, which in other words it means that the n functions by 1 by 2 by n will be called linearly independent if C1 by whenever C1 by 1 plus C2 by 2 plus Cn by n is 0, it will always imply that C1, C2, Cn all are zeros. Now let us see how we can check the linear dependence independence of functions. From the definition of linear dependence it follows that if you take n equal to 2 here, that means if you take two functions by 1x and by 2x, then they will be linearly dependent provided C1 by 1 plus C2 by 2 equal to 0, where both C1 and C2 C1 C2 both are not 0. That means at least one of them is non-zero. So suppose C1 is non-zero, then C1 by 1 plus C2 by 2 equal to 0 can be written as, so let C1 be non-zero, then we can divide by C1 and write by 1 equal to minus C2 by C1 into by 2. So C2 by C1 minus C2 by C1 is a constant, so we can write R by 1 equal to some constant k times by 2, which will mean that by 1 is a scalar multiple of by 2. In particular, the two functions, let us say by 1 and by 2, they will be called linearly dependent on some interval I if they are proportional, that is by 1 is k times by 2 or by 2 is equal to k times by 1, because when we would take n equal to 2 in this definition, then if by 1 and by 2 are linearly dependent, then C1 by 1 plus C2 by 2 will be equal to 0, where C1 and C2 are not both zeros. So suppose C1 by 1 x plus C2 by 2 x equal to 0, where let us say C1 is not equal to 0, then we can write by 1 x equal to minus C2 over C1 into by 2x. Minus C2 over C1 is some constant, so we can write R by 1x equal to some constant k times by 2x, where k is equal to minus C2 over C1. So by 1 is a constant multiple of by 2. If instead of C1, let us say C2 is equal to 0, okay, C2 is not equal to 0, let us say C1 is equal to 0, then C2 must be not equal to 0. So if C2 is not equal to 0, then we can divide this equation by C2 and write, we may write by 2 is equal to minus C1 by C2 into by 1x. So this will be some constant, let us say some constant R, so R into by 1x, where R is equal to minus C1 by C2. So in either case, by 1 and by 2 will be proportional to each other. One will be a constant multiple of the other. Now if by 1 by 2 are not proportional on I, then they will be linearly independent on I. For example, if you take the function by 1x equal to sin 2x and by 2x equal to sin x into cos x, then we know that sin 2x is 2 sin x cos x. So we can write by 1x to be equal to 2 times by 2x, which means that by 1 is a scalar multiple of by 2, and so by 1 and by 2 will be linearly dependent on the interval minus infinity infinity. Now in example 2, suppose we take the function by 1x equal to x and by 2x equal to mod of x, then we can see from the graph that they are not linearly dependent on the interval minus infinity infinity. By 1x is equal to x, the graph of by 1x equal to x is this line, this is by 1x equal to x, and the graph of by 2x equal to mod of x, this is by mod of x graph. So we can see that x is not a scalar multiple of mod of x. If x is suppose if x is equal to mod of x, then x is not a equal to some constant times mod of x, because mod of x is equal to x when x is positive and minus x when x is negative. So x and mod of x cannot be equal for some constant k, therefore they are both linearly independent on the interval minus infinity infinity. Now we take the case of say 4 functions, by 1x equal to cos square x, by 2x equal to sin square x, by 3x equal to sec square x, and by 4 equal to tan square x. We can see that they are linearly independent on the interval minus pi by 2 to pi by 2. So this interval is very important here, because you can see that this is sec square x is 1 over cos square x. So if we go beyond minus pi by 2 to pi by 2, then what will happen is that sec square x is 1 over cos square x, it will be 0 at pi by 2 and minus pi by 2, so sec square x will not be defined. So we can find ourselves, and moreover in tan square x will not be defined at pi by 2 and minus pi by 2, so we will consider the interval minus pi by 2 pi by 2. Now here let us see, we have by 1 equal to cos square x, by 2x equal to sin square x, by 3x equal to sec square x and by 4x equal to tan square x. We have to show that they are linearly dependent on the interval minus pi by 2 to pi by 2. So what we do is we have to find our constant C1, C2, C3, C4 such that which are not all 0, such that C1 by 1 plus C2 by 2 plus C3 by 3 and C4 by 4 is equal to 0. So we have to find constants C1, C2, C3 and C4 not all 0, such that C1 by 1 plus C2 by 2 plus C3 by 3 plus C4 by 4 is equal to 0. So what we do is C1 by 1 is cos square x, so C1 times cos square x, then C2 times sin square x, then C3 times sec square x, and then C4 times tan square x. We know that sec square x is 1 plus tan square x, so and moreover we know that sin square x plus cos square x is 1. So let us choose C1, C2 to be equal to 1, so that we have here cos square x plus sin square x, that is 1, and here we will have C3 into 1 plus tan square x. So let us take C3 to be minus 1. Okay, so let us take C1, C2 to be equal to 1, C3 equal to minus 1 and C4 equal to 1. Then we can see that cos square x plus sin square x minus sec square x plus tan square x will be equal to, this is 1 minus 1 plus tan square x plus tan square x. So this will be equal to 0. So we are able to find the constants C1, C2, C3, C4 not all 0, such that C1 by 1 plus C2 by 2 plus C3 by 3 plus C4 by 4 is equal to 0. So they are linearly dependent on the interval minus pi by u to pi by 2. And in the example 4 we consider by 1x equal to e to power x, by 2x equal to e to power 2x and by 3x equal to e to power 3x. Let us show that they are linearly independent on the interval minus infinity to infinity. So in order to prove that they are linearly independent, we have to show that whenever we write C1 by 1 plus C2 by 2 plus C3 by 3 equal to 0, it will always imply that C1, C2, C3 all are zeros. So let us say let C1 by 1 plus C2 by 2 plus C3 by 3 is equal to 0. That is C1 e to the power x plus C2 e to the power 2x plus C3 e to the power 3x equal to 0. Our aim is to prove that C1, C2, C3 all are zeros. Now we know that C1 e to the power x is always positive for every real x. We know that e to the power x is greater than 0 for all x belonging to R. So what we do is we divide this equation by e to the power x. So dividing the equation 1 by e to the power x, we have C1 plus C2 e to the power x plus C3 e to the power 2x equal to 0. Again divide this equation by e to the power x. So we have C1, now what we will do is, let us differentiate this equation. This equation holds for every x belonging to R. So differentiating this equation with respect to x, differentiating with respect to x, we have we get this is 0, C2 e to the power x plus C3 into 2 times e to the power 2x. So, we get this. Now, what we do is we again divide by e to the power x. So, dividing by e to the power x, we will get C2 plus 2C3 e to the power x equal to 0. Again this equation is valid for every x belonging to R. So, differentiating with respect to x, we get 2C3 e to the power x equal to 0. Now, e to power x is always positive. So, this means that C3 equal to 0. When C3 is 0, from here we get C2 equal to 0, and then C3 and C2 equal to 0 give us C1 equal to 0. So, we get C1, C2, C3 all are zeros. So, e to power x, e to the power 2x and e to the power 3x, they are linearly independent functions on minus infinity to infinity interval. Now, let us consider the n functions. So, suppose we have n functions by 1x, by 2x, by nx. We have seen while doing these examples that it is not easy to check the linear dependence independence by finding the constant C1, C2, C3, C4 and so on. So, it is so there is another process by which we can check the linear dependence independence of n functions. So, if suppose we have n functions by 1, by 2, by n which possess say at least n minus 1 derivatives with respect to x, then we will check the value of this determinant. This is nth order determinant which we denote by w by 1 by 2 by n, and call is at the Wronskian of these, call it as the Wronskian of these n functions. So, in the first row we have by 1 by 2 by n, second row has first order derivatives of by 1 by 2 by n, and the last row has n minus 1th order derivatives of by 1 by 2 by n. We will see that this nth order determinant, okay, in the case of in the case of n functions by 1 by 2 by n, which are the solutions of the homogeneous linear nth order differential equation, they will be linearly independent if and only if the Wronskian of these n functions is not equal to 0 on the interval I. So, it is easy to check the value of the Wronskian of the n solutions of the nth order linear differential equation to decide whether they are linearly dependent or independent. Let us see how we prove this result. So, let us consider an initial value problem. Here this is called an initial value problem because we have a second order differential equation with two conditions, by at x naught equal to y naught, by dash at x naught equal to y 1 which are called the initial conditions. So, a second order differential equation of with two initial conditions is called as an initial value problem. So, let us consider this initial value problem. If fx and gx are continuous functions here on an open interval I, then this initial value problem has a unique solution by x on the interval I. This is a standard result. So, we shall make use of this result. Let us suppose that the coefficients fx and gx of this differential equation are continuous in an open interval I, then any two solutions of this equation are linearly dependent on the interval I if and only if their Wronskian is 0 for some x equal to x naught. If w is 0 for some x equal to x naught, then w is identically 0 on an I. So, here this is a homogeneous linear differential equation. The two functions by 1 and by 2, let us say, the two solutions by 1 and by 2 of this differential equation will be linearly dependent if and only if their Wronskian is 0, identically 0. So, this result can be extended to n functions. We are proving it for n equal to 2. So, in the case of nth order differential equation, the n solutions will be linearly dependent if and only if their Wronskian is 0. So, we will do it for simplicity, we will do it for n equal to 2. So, let us see how we prove this result. So, let us assume that let us assume that by 1 and by 2 be two solutions of the equation 2 which are linearly dependent. Let by 1 and by 2 be two solutions of the given equation which are linearly dependent. Then by the definition of linear dependence, then there exists constants K1 and K2 say not all 0 such that K1 by 1 plus K2 by 2 is equal to 0. So by the definition of linear dependence, we arrive at two constants K1 and K2 which are not both 0 such that K1 by 1 plus K2 by 2 is equal to 0. We have to prove that the Wronskian of the functions by 1 and by 2 is equal to 0 for some x equal to x naught in I. So we can see from here that then K1 by 1 dash plus K2 by 2 dash is equal to 0. Differentiating this equation with respect to x, we have K1 by 1 dash plus K2 by 2 dash is equal to 0. So from these two equations what we have, by 1 by 2 by 1 dash by 2 dash, this coefficient matrix into K1 K2 So this is a homogeneous system of linear equations. This is a homogeneous system of linear equations where K1 K2 are not both 0, therefore determinant of this matrix must be 0. So this implies that modulus of this by 1 by 2 by 1 dash by 2 dash must be equal to 0. So the determinant of the functions by 1 by 2 by 1 dash by 2 dash is equal to 0, that is the Wronskian of the functions by 1 by 2 is equal to 0. So this proves that whenever the two functions by these two solutions by 1 by 2 of the equation 2 are linearly dependent, then their Wronskian is 0. So it is 0 for some x naught. Now let us see, we can prove the converse. So for the converse, let us assume that the Wronskian W is 0 for some x equal to x naught in I. So W x naught, W by 1 x naught by 2 x naught is equal to 0, that is by 1 x naught by 2 x naught by 1 dash x naught by 2 dash x naught is equal to 0. We are given that the two solutions by 1 and by 2 of the equation 2 are such that the Wronskian W is 0 for some x equal to x naught. So from from that we have this determinant equal to 0. Now let us consider the system of equations. Consider the system of equations K1 times by 1 x naught plus K2 times by 2 x naught let us consider this system of equations. So here we see, since the determinant of k1 x naught, since the determinant of by 1 x naught, by 2 x naught, by 1 dash x naught, by 2 dash x naught is equal to 0, this homogeneous system of linear equations implies that k1 and k2 are not both 0. Okay, so this implies that k1 and k2 are not both 0. And now then let us define by x equal to k times by k1 times by 1 x plus k2 times by 2 x. Since by 1 and by 2 are solution of the equation 2 and equation 2 is a homogeneous equation, by the superposition principle it follows that k1 by 1 plus k2 by 2 is also a solution of equation 2. So by x is also a solution of equation 2. Now from these equations it follows that y at x naught is equal to 0. If you put x naught here, k1 by 1 x naught plus k2 by 2 x naught is 0. So by at x naught is equal to 0 and by dash at x naught is also 0. By dash at x is equal to k1 by 1 dash x plus k2 by 2 dash x. When you put x equal to x naught and use this equation, we get by a dash at x naught equal to 0. So now what do we see? That by x is a solution of equation 2 and also that by at x naught is 0, by dash at x naught is equal to 0. Now another solution of equation 2 is by star equal to 0 solution, that is 0 solution satisfies the equation 2 and also by dash is equal to 0 satisfies by dash at x naught equal to 0, by dash by star dash at x naught equal to 0. So this solution satisfies equation 2 along with the two conditions that at x naught it is 0 and its derivative also vanishes at x naught. Now let us apply the theorem uniqueness theorem, existence uniqueness theorem. This theorem tells us that in when we have this homogeneous equation or we have this initial value problem where y at x naught is y naught, y dash at x naught is y1, then the solution is unique. The initial value problem has a unique solution. So both the solutions by x and this solution must be identical and therefore by star must be equal to y. So thus we can say that y must be identically 0. So k1 by 1 x plus k2 by 2 x is equal to 0 for all x belonging to I. So by the uniqueness theorem it follows that k1 by 1 plus k2 by 2 is equal to 0 for all x belonging to I and k1 k2 are not both 0. This implies that by 1 and by 2 are linearly dependent. By 1 and by 2 are linearly dependent. Now by 1 and by 2, so by 1 and by 2 are linearly dependent. So whenever Wronskian W is 0 for some x equal to x naught, we have proved that by 1 and by 2 are linearly dependent. Now let us apply the proof of the first part. In the proof of the first part we have shown that whenever two solutions are linearly dependent then W is identically 0. So here by 1 and by 2 are linearly dependent. Now use the proof of the first part to say that W is 0, W is identically 0 on I. So now using the proof of the necessity part, we have W is identically 0. So this theorem tells us that whenever two solutions of equation 2 are linearly dependent then W is identically 0 on I. Here the continuity assumption in this theorem cannot be omitted. Let us see why the continuity assumption cannot be dropped here. This is evident from this example. Let's take by 1 x equal to x cube for all real x, and by 2 x equal to x cube when x is greater than or equal to 0, and minus x cube when x is less than 0. You can easily check that by 1 x equal to x cube satisfies this equation for all real x, and by 2 x equal to x cube when x greater than or equal to 0, and minus x cube when x less than 0, they also satisfy this second order differential equation for all x. So both by 1 and by 2 are. Now moreover we can see that by 1 x is x cube for all real x, while by 2 x is x cube when x is greater than or equal to 0, minus x cube when x is less than 0. So they are both linearly independent on the x axis. One is not a scalar multiple of the other. Although their Wronskian is identically 0, we can easily check that Wronskian of by 1 and by 2 is identically 0. So this does not contradict the theorem 3. Here we are seeing that although the functions by 1 by 2 are linearly independent, their Wronskian turns out to be identically 0. This example does not contradict theorem 3 because the coefficients in this equation fx is minus 3yx and gx is 3yx square, they are not continuous at x equal to 0. So because of the fact that they are not continuous at x equal to 0, it does not contradict theorem 3. Now when suppose we consider the nth order homogeneous linear differential equation where a1x, anx are continuous functions, then the result which we proved for n equal to 2, this result can be generalized to n functions. So we have the set of solutions, n solutions by 1 by 2 by n is linearly independent on I if and only if w by 1 by 2 by n is not equal to 0 for every x in I. So that can be generalized to this nth order homogeneous linear differential equation. Now a set by 1 by 2 by n of n linearly independent solutions of the homogeneous nth order differential equation on interval I is called a fundamental set of solutions, and it can be shown that there exists a fundamental set of solutions for the homogeneous linear nth order differential equation on an interval I. As an example, we can consider the set of solutions sin 2x, cos 2x, e to the power 2x. These three functions we can easily check that they are solutions of this third order homogeneous linear differential equation, and they form a fundamental set. Fundamental set means we have to show that the three functions are linearly independent, which we can easily show by using the Wronskian. So let us consider the Wronskian of these three functions and show that these three functions are linearly independent and so form a fundamental set. So let us consider the Wronskian of these three functions. So Wronskian say that let the functions by 1 be equal to sin 2x, by 2 be equal to cos 2x, by 3x be equal to e to the power 2x, then w by 1 by 2 by 3, this is equal to e to the sin 2x, cos 2x, e to the power 2x. Next row contains the derivatives, so 2 cos 2x, this will be minus 2 sin 2x, then here we will have 2 e to the power 2x, and here second order derivatives of each of these functions. So we have 4 minus 4 sin 2x, and then here we have cos 2x into minus 4 cos 2x, here we will have 4 e to the power 2x. Now e to the power 2x is strictly positive, so we can take e to the power 2x out of the last column, so e to the power 2x, and then we can take common from last column, and then we take 2 and 4 from the first and second and third row. So I will have here 8 times what I have done is I have taken e to power 2x common from the third column and 2 and 4 from the second and third rows. So 8 times e to power 2x. Now let us add first row to the third row. So we will get here 0, 0 and we will get here 2. Now let us expand it by the last row. So we will have here 8 e to the power 2x into 2 times minus sin square 2x minus cos square 2x. Which is minus 1, so we get minus 16 e to the power 2x, which is in fact less than 0. So the Jacobian is not 0 and therefore the three functions are linearly independent and so form a fundamental set of solutions of this third order differential equation. Now this last theorem tells us that if you take y equal to c1 by 1 x plus c2 by 2 x and it be a general solution of the homogeneous equation 2 then it includes all solutions of equation 2. So let us see how we get this. Let y equal to c1 by 1 plus c2 by 2 be a general solution of equation 2 on an interval I where the coefficients fx and gx are continuous, and y be any solution of equation 2 containing no arbitrary constants, then this y is obtained from 4 by assigning a suitable value to the constants. So this general solution includes all solutions of the equation 2. So this is what is conveyed by this theorem. With this I would like to conclude my lecture. Thank you very much for your attention.